We are at a ski resort now, and water is being pumped from a base of a mountain up 4,286 feet to a snowmaking machine. They give us the length of the pipe, they give us the diameter of the pipe, and they say that the pressure at the outlet, at 2 in this case, needs to be 180 psi. So I do a quick little doodle here to help with what we're trying to do. Let me go ahead and draw out the Bernoullis that we're going to use. And then I'm also going to include the pump, in this case, the head of the pump. And later we are going to convert that over to horsepower. And then we have P2, specific weight, velocity, elevation, and then our losses. Our losses due to the 2,000 foot long steel pipe. So for that case, I'm going to go ahead and write down our losses there. So we can do some simplifications here, here, here. And then we have a pressure 2, we have some outlet velocity, we have some Z2, so everything else seems fine. In this case, V2 is going to be equal to the velocity through the pipe, so those are going to be the same velocities here, don't have to worry about that. But let's go ahead and find out what that velocity is. So that velocity, in this case, is flow rate divided by area. I was getting ahead of myself, I was writing down pi. Now let's do it. So 0.26 cubic feet per second divided by pi over 4, and the diameter in this case is 3 inches. I'm going to convert that over to feet squared. When you go through that calculation, you will get 5.30 feet per second. So we have that. And then we need to figure out the friction with respect to the losses. We need to calculate that. So one of the things we need to calculate is Reynolds number, and the other thing that we need to calculate besides Reynolds number is the ratio of the roughness to diameter. So we have those two things we've got to do. So let's we look up for steel pipe, its roughness 0.00015 feet, and then the diameter, converting that to feet, you'll get roughness of 6 times 10 to the negative 4th. So we have that. Reynolds number is on our list to do as well. So we have our velocity, which we already calculated, 5.3 feet per second. Diameter, in this case, converting that to feet. And then with respect to our kinematic viscosity, if you look it up for water, this is the value you will get. Calculate, you will get 7.96 times 10 to the 4th for a Reynolds number. So then from the Moody diagram or the Moody chart, you will get a friction factor. With the roughness and with the Reynolds number, you will get 0.0212. All right, so we have that. Now the next thing that we can do is we can go ahead and start plugging in to our expression and solving for the pump head, and then we'll convert it to horsepower later. So the pressure in this case is 180 pounds per square inch, but we need to multiply and get rid of the square inches and convert it over to square feet. So we have that as our pressure, and then divide by the specific weight, 62.4 pounds per cubic foot. So that's the pressure portion. And now the velocity portion that we're going to have, so that'll be 5.3 feet per second, that squared, divided by 2 times gravity, 32.2 feet per second squared. Now, what I'm going to do here is I'm going to go ahead and highlight this and this. And that is what this is. All right? Now, what I'm going to do is 1, right? And I'm factoring. That's all I'm doing. I'm just factoring. And then let me make this a square bracket to make this a little bit more clear. And then we have our friction, 0.0212. And then the length, 2,000 feet, over our diameter converted to feet. So now we have those two terms taken care of. And then we have elevation. So we have 4,623. You know what? I misread the problem. I verbally said it. So let me make some adjustments here. I made a mistake here. Z1 is not 0. I apologize for this. So let me change this up. I completely misread the problem. So but we can make our adjustment here. All right, so 4,623 feet minus 4,286 feet. There we go. So that's the adjustment calculation there. And then when we go through that calculation, you will get that the pump head will be 827 feet. Now we have to convert this over to horsepower. So power is the same as specific weight, volumetric flow rate, and then pressure head. So in this case, we will have 62.4 pounds per cubic foot for our specific weight. Our volumetric flow rate, 0.26 cubic feet per second, and then 827 feet for our head. And then this will give us 13,420 foot-pounds per second. And if you convert that over to horsepower, it'll be 24.4 horsepower.